In addition to these like calculus laws, we have thermodynamic relations also we can use. And again, thermodynamic relations, we have fundamental property relations, we have Maxwell relations, and we have some relations we explained in previous chapters. So if we start with the fundamental property relations, so if we recall the energy balance equation for closed system, this is the energy balance equation for closed system. The change of internal energy equal the amount of heat added or removed from the system plus the amount of work done by the system or removed by the system. If you remember chapter 4, when we start talking about the entropy, we have a relationship relating entropy to heat. So we have dQ is TdS. And if you remember chapter 1, the work that we calculated is negative PdV. So if we put these two equations together, then we will have du is TdS minus PdV. Okay. And again, if you remember, all the properties we have in this equation are extensive or intensive properties. Anyone remember the difference between them? One of them depends on the mass or the size of the system. Do you remember which one? Extensive or intensive? Extensive. And we don't like to work with the extensive properties, especially in mathematical model. So we need to convert all of these equations. So divide all the properties by the number of moles. So this is why we have the molar internal energy equal T times molar entropy minus P molar volume. And this is fundamental property relation for molar internal energy. So this is the first fundamental property relation that we can have. If you can have internal energy, or you can have entropy, or you can have volume, you can like replace them based on this fundamental property relations. Okay. From this fundamental property relation, we can understand that the internal energy is function of entropy and molar volume. Okay. If you change the entropy, the internal energy will change. If you change the molar volume, the internal energy will change. So now if we get back the total derivative, so if you try to do this, this shows how it looks like. So du, the total change we have in the entropy is like two things. The change of the entropy with change in, internal energy change with entropy, plus internal energy change with specific volume. Okay. So now we have two things. We have du, we calculated from the fundamental property relations. We have du, we have calculated from the total derivative, basic law of calculus. So these two equations should be similar, right? Or should be equal. So if we compare these two equations together, then we can say du is TdS minus PdV. This is the fundamental property relation, equal all of this from the total derivative. If you compare these two equations, then you can conclude that du by ds at constant V, all of this partial derivative is equivalent to what? Temperature. Du by dV at constant S, all of this is equivalent to minus P. And this is what we need to do in the mathematical derivation. So in the mathematical derivation, you have many partial derivatives. So at any step, if you see du by ds at constant V, directly remove it, put it temperature. If you have du by dV at constant S, remove this partial derivative and put negative P. Clear? Okay. So this is the first fundamental property relation. We have other fundamental property relations. We have four fundamental property relations. Okay. First one, internal energy. Second one, enthalpy. And this is the how it looks like. H is U plus PV. If you take the derivative, so we have dH is du plus dPV. Again, this is derivative of two variables. So basic calculus, it says dxy is x dy plus y dx. So this one dPV will be PdV plus VdP. So we have this equation here, and again, from the fundamental property relations, the first one, du is TdS minus PdV. So put all of this together. Put or remove du, and put this equation instead of it. Put this term or remove this term and put this one, then we'll have dH is TdS minus PdV. This is this term here, which is du. And this is from the derivative of two variables. Then we have dH is TdS plus PdV. And this, the fundamental property relation for molar enthalpy. We can play the same thing. Here, enthalpy is function of entropy and pressure, right? So we can put the same equation in the total derivative like formula, and if we did this, then we will have, this is the equation, h is function of s and p, put the total derivative, then we have these two equations together, and then you can say dH by ds at constant pressure, this is equivalent to what? dH by ds at constant pressure, this partial derivative equivalent to, someone is saying it, temperature, and dH by dB at constant entropy, this is molar volume. Okay? So again, in the derivation, if you find at any time this partial derivative, remove it and put temperature. If you find this partial derivative, remove it and put molar volume. Clear? So if we continue to do the same thing for the other fundamental property relations and play with this basic calculus, again, this derivation, like I will not ask you to make the derivation, but it's very important to know this one. Okay, and again, it's not important to memorize them, but how you can use them in the derivation. We have other two fundamental property relations, one for Gibbs free energy, one for Helmholtz equation. This is the first one. This is the second one, if you put it in molar volume. So we have these other like fundamental property relations. One for Gibbs free energy, one for Helmholtz equation. So we have four fundamental relations. One for internal energy, enthalpy, Gibbs free energy, Helmholtz equation. Do the same thing for all of them, and as a summary, this will be everything that you need to have. Okay, so from property relation number one, so du by ds at constant v, this is temperature. Du by dv at constant s, this is minus p. This is the fundamental property relation number two. These are what the conclusion of fundamental property relation number three. This is fundamental property relation number four. Clear? So this is the first part of the like the fundamental property relations. So this tells you that some partial derivatives in your model, you can remove them and put one property, like temperature, like pressure, like molar volume. Okay, but not all the partial derivatives are equivalent to like a direct thermodynamic property. So in this case, you can think of something called Maxwell relations. And Maxwell relations, if you like start doing this one, Maxwell relations, the whole idea is we need to replace the partial derivative that we cannot solve with another partial derivative that we can solve. So always keep in your mind, so your goal in the mathematical modeling is to remove the partial derivative. The priority number one or step number one, replace the partial derivative with a thermodynamic property. Remove the whole partial derivative and put like temperature, put pressure, put volume. If this is possible, this is fine, go with it. If this is not possible, then remove the partial derivative that you cannot solve with another partial derivative that you can solve. And now here the Maxwell relations play this role. So Maxwell relations come from the fundamental property relation. So we said this one here, we have like this, what we have explained or what we obtained from the fundamental property relation. Okay, so if we have this one, and if we decide to like get the derivative of this one at constant v, so we have du pi dx as constant v, this one here, which is this one. So all of this partial derivative, take the derivative when v change with when entropy is constant. And again, here for the temperature, make the same thing, d pi dv at constant s. So for everything here, we are doing this. Take d pi dv at constant s, d pi dv at constant s. And same thing here, we have du pi dv at constant s, so take the derivative, the d by ds at constant v, d pi ds at constant v. So if we did this, then you can see the following. You can see here we have du, how I put it, here I have du and here I have du. Okay, here I have dv ds, and here I have dv ds. And if you remember from basic calculus, this is the second derivative, and the second derivative, these will be constant regardless of the arrangement. Like du by dv ds, this is the same as du by ds dv. So since these are constant, the second derivative, then we can say this one or this group is equivalent to this one. This is what we are trying to do here. And this is the first Maxwell relation. If you have partial derivative, then this partial derivative is not equivalent to any direct thermodynamic property. So there is a possibility that this partial derivative is equivalent to another partial derivative. So we can replace partial derivative we cannot solve with another partial derivative we can solve. Okay? So this is the whole idea of Maxwell relation, and this is how it's developed. You can repeat the same thing for the whole fundamental property relations. And if you did this, if you apply this concept, then you will see these are all fundamental or Maxwell relations we have. Clear? So again, so what we did so far, so we have, or we need to develop mathematical models. In order to develop mathematical models, we have some basic calculus laws that we need to keep in our mind. The whole idea that these basic calculus laws will end up with partial derivatives. And your model cannot contain any partial derivative. So if you find any partial derivative, we need to remove it. How we can remove it? So the first thing you should think of it, if you can replace the partial derivative with a thermodynamic property. And this is the whole idea of fundamental property relations. Okay? If this is possible, go for it. If it's not possible, then replace the partial derivative with another partial derivative. And this is Maxwell relations. So you can use any of these combination here. Any partial derivative, remove it with any partial derivative. And one of the things that to keep in your mind, always we prefer that we need to have partial derivative contains v, t, and p. These are the three variables we like to have in partial derivative because easily we can solve this partial derivative. Because p, v, t, these three variables are combined together in the equations of a state. Do you remember chapter 7 that we explained after chapter 1, the beginning of the semester? So we have equations of a state. Equations of a state, these are equations that relates pressure with temperature and molar volume. So if you have any partial derivative contain these three variables, we can obtain the value of this partial derivative from the equations of a state. I can tell you use the ideal gas equation of a state, use Ping-Robinson equation of a state, use Suave equation of a state in order to find the value of this partial derivative. But if you have any partial derivative that contains entropy, for example, contains internal energy, or we have one property at constant entropy similar to this one, we can solve these equations using, we can solve this partial derivative using the equation of a state. So keep with your mind of these things because this is what you will see in the model and this is how we are thinking while we are working on this model to develop the final form. Clear? So this is the second part. This is the Maxwell relations we have here. And again, this is the summary of all the equations we have and the way of how we are driving it. Okay? The last thing that we will say today, we have previous equations we explained before, including heat capacity, 3 equations. One of them is containing something called coefficient of thermal expansion. Coefficient of thermal expansion, this is a property that tells you how the molar volume of any substance will change if you have temperature changes at constant pressure. And this is the equation of it. So coefficient of thermal expansion is 1 over molar volume times how the molar volume will change with temperature at constant pressure. So at any time, if you see this partial derivative, VTP, one of the options to replace it is the coefficient of thermal expansion. Coefficient of thermal expansion is a property that we can find, and this property is very important in the design and constructing any equipment. Second thing, we have something called coefficient of isothermal compressibility. So this one. This tells you how the changing the pressure affecting the molar volume. Okay. And again, it has equation for this one, coefficient of isothermal compressibility is minus 1 over V dV pi dP at constant temperature. So again, this group can be replaced with coefficient of isothermal compressibility. And the last thing we have from chapter 1 is heat capacity. And if you remember, we have two heat capacity values: heat capacity at constant volume, heat capacity at constant pressure, and this is the relations for both of them. Clear? So to wrap up everything, so we have many mathematical equations, many mathematical laws we have in this chapter, and the whole idea is how we can use all of these laws, all of these like rules and relations in order to derive an equation, simple equation. We can substitute in this equation in order to find any thermal property that we need to calculate. All of the steps we will use in this chapter in case if you don't have appendix, if you don't have figures. Okay? Is it clear? Any questions?